Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at the homework for lesson 6.2.2. This is highlighting the corresponding parts of similar shapes. Now, first things, make sure we understand the difference between whether shapes are similar or whether they're congruent to each other. The similar shapes have the same shape, but not necessarily the same size. So if you look at these two triangles, triangle ABC and triangle DEF, they appear to be the same shape, but one is clearly bigger than the other. So they would be considered similar, not congruent. When you have congruent shapes, they're going to be both the same size and the same shape. So they will be similar, but they are going to be the same size as well. So when you take a look at two triangles, you look for the corresponding parts and you check to see whether or not they're exactly the same length. You look at the corresponding sides and the corresponding angles. So let's come back, since this is really focusing on similar shapes, the corresponding sides and the corresponding angles. So if the two corresponding parts are in the same position, given the orientation of the two triangles, you look at triangle ABC, angle A is in the same position as angle D. Angle B is in the same position as angle E, and angle C is in the same position as angle F. Let me put 3 of those in there. So the corresponding angles have the exact same measure, but the corresponding sides do not. So these two sides are not the same length, but they do correspond to each other. So if you recall from the lesson, at the very beginning of the lesson that we talked about yesterday, you are, what am I saying? They are not the same length, but they are proportional, and their proportionality is defined by a scale factor. Okay, so if this was 5 and this was 10, then the scale factor would be 2. If this was 5 and this was 7.5, then the scale factor would be 1.5 or 1.5. Okay, so finding the corresponding sides. Oops, maybe I don't want to do that. Let me do this and that. We'll just go ahead and get rid of those. Now, when you're taking a look at two triangles that are not oriented the same, this is where the rigid transformations come into play. You want to be able to visualize rotating one or both of these, or maybe reflecting them as well. But generally what I do is this. I look for, like, if there's a right angle, where are the right angles? I look for the longest side of each one, the shortest side for each one, and then you can, determine the other side. So by looking at it this way, identifying the angles that are obviously the same, and the right angles would qualify as that, and then look at the sides that appear to be proportional or corresponding, right? The shortest ones should correspond to each other. The longest ones would correspond to each other, and so on and so forth. So once you've got that down, then you can solve the problem. So you know, in this situation, that the shortest side here corresponds to the shortest side here, so the scale factor going from the smaller to the larger would be 2. And if you were going from the larger to the smaller, the scale factor would be 1/2. And does that apply here as well? 2 times 2 is 4? Yes, it does. Okay, so you got to picture it in this way and think of our rigid transformations from the beginning of chapter 6 to help you reorient, at least in your mind, these triangles so you can get the corresponding parts matched up. All right, it says create a large, for problem number 58, create a large coordinate graph on graph paper and graph the triangle at the right. So here's 0.13, 4.2, and -2, -2. Multiply the y-coordinate, only the y-coordinate, by 4. And so what is going to happen here? Are we going to get a proper dilation with similar figures? And the answer to that is no. When you double or triple or quadruple one coordinate, but you don't multiply the exact same number times the other coordinate, you are not going to get a properly dilated similar figure. You're going to get a distorted image. And so by multiplying the y value by 4, but keeping the x values the same, essentially what you did is you stretched out your shape vertically, not horizontally. So if you picture this as like a mirror at a carnival, when you're looking at it, if the mirror is somewhat programmed for your vertical height to be stretched, but not your horizontal width at the same rate, then you're going to look tall and skinny in the mirror, and that's what happened essentially here. So they are absolutely not congruent to each other. The corresponding angles are not congruent. We're not getting anything that's congruent to the original. Okay, now moving in a different direction. Lashaya is famous for her delicious brownies, which she sells at football games. The graph on the right shows the relationship between the number of brownies she sells and the amount of money that she earns. Okay, so we're not talking necessarily profit here, because I'm sure she probably had to buy the supplies, and so those are not accounted for here. So this, I believe, is simply a proportional relationship for the number of brownies that she sells and the amount of money that she brings in. This is not a statement of profit. So knowing that 0, 0 absolutely applies here, and then 12 brownies, she made $21.60, then we should just be able to take in this situation and say, all right, $21.60 divided by 12 will tell you the price per brownie, and it ends up being $1.80 per brownie. Okay, now does that look like it kind of makes sense here, where if you sell 10 brownies, that would be somewhere around 18. It's hard to tell with the scaling of your y-axis, but it looks like it could be somewhere around there. And that definitely is the case. Okay, so remember, how do we find the unit rate? Well, if you know it's $21.60 for 12 brownies, we're trying to find out how much it's going to be for one brownie, and that's why we divide $21.60 by 12 to figure out our unit rate. And so it says, during the last football game, Lashaya made $34.20. How many brownies did she sell? Okay, well, let's go ahead and write in $34.20 over X. You can solve it this way if you want to. Look for what do you multiply times 2160 to give you $34.20, or what you might do is this. You might set up the equation where the amount of money that you make is based on the fact that every brownie costs $1.80 times X. So if we know the value for Y, $34.20, then we can solve for X by taking this number and dividing it by our unit rate. I'll go ahead and show the work. $34.20 divided by our unit rate of $1.80 per brownie. No, no, no. $1.80 per brownie, and you get 19 brownies. So absolutely 19 brownies were sold. That's how she raised $34.20. All right, let's look at this. Figure 3 of a tile pattern has 11 tiles. I went ahead and wrote that right there. Figure 4 has 13 tiles. Okay, so can we figure out whether or not this is growing at a constant rate? Oh no, it tells us it's growing at a constant rate. So we know that this formula of y equals mx plus b is going to apply. So once we figure out what the equation is, we can now figure out how many tiles will be in any figure, or if you give me a number of tiles, I can tell you which figure number would have that number of tiles. Okay, so once again, you can set up a table and you can say, oh, it looks like the growth rate is increasing by 2 every single time. So when we work our way backward, we get to our y-intercept, which is 5. That's how much we started with figure 0, and it grew by 2 every single time. So if y equals 2x plus 5, then we're going to say, all right, well, the 1015th figure, oops, stop that, is going to require us to take away 5 from each side and then divide by 2. And when you divide 1010 by 2, you get 505. So absolutely nobody wants to create a table that goes all the way to the 505th figure, right? That's why we use algebra and we create rules. All right, normally the longer you work for a company, the higher your salary per hour. Hector surveyed the people at his company and placed his data in the table below. Okay, now this kind of assumes They're probably union workers because it looks like everybody gets the same raises for whatever year they're working. Okay. In many businesses that are non-union, people get rewarded with raises for their work performance, not just based on how long they've been working there. So yeah, whatever. Not sure why I went down that road. Hooray for unions. Okay. So use Hector's data to estimate how much he makes, assuming he has worked at the company for 12 years. Okay. So in 1 year, he made $7. In 2 years later, he got a $1.50 raise. So how much is the raise there? It looks like it's about 75 cents per year, right? So if you take the change in Y, let's call this Y, and that's X. X would be the number of years. The growth rate is going to be the change in Y over the change in X. So Y went up from here to here by $1.50 in 2 years, which means that they must be making 75 cents per year for the growth rate. Okay, so if we work backwards, that means that when they were hired, they must have made $6.25. Right? So every year it increases by 75 cents. Do we see that 75-cent growth there? Yes. 75 cents plus $10.25 is $11.50. Okay. So our rule must be Y is equal to 0.75. Every year working, they get a 75-cent raise, plus the original starting wage was $6.25. So if he works for 12 years, you're going to take 12 times 75 cents. 12 times 0.75. That's $9 plus the original wage that they made. $15.25 would be the new wage that they were earning after 12 years of work. Hector is hiring a new employee who will work 20 hours a week. How much should the new employee earn for the first week? Okay, so the fact that they're a new employee means that this is their wage right there. They started out at $6.25, multiply that times 20, and they should make $125 per week before taxes and other wonderful deductions are made to their paycheck. All right, Mr. Greer solved the problem or the equation as shown below. So this is similar to what we did yesterday, where there's a mistake that was made. So showing your work allows you to go back and review your work to determine if it's obvious what your mistake was, if you made a mistake. First of all, you would have to check the solution to know whether or not you made a mistake or not. So if X is equal to 1/4, then you should be able to plug it in here and get both sides equal to each other, but they are not. So where was the mistake? So 4x is equal to 8 times this quantity, 2x minus 3. After using distributive property, it looks like he multiplied 8 times 2x, but not times the -3. So there's your problem. So what we want to do is send in the dive bombers and rewrite this as 16x minus 24. And then I would just go ahead and subtract 16x's from each side, because that's going to be the most efficient way to solve this. And you get negative 12x is equal to negative 24. So what do you multiply times negative 12 to give you negative 24? You multiply times 2. So that should be the solution. X is 2, not 1/4. So let's double check that here. 4 times 2 is 8. That's supposed to be equal to 8 times 2 times 2 is 4. 4 minus 3. And 4 minus 3 is 1. So 8 times 1 is equal to 8. That is correct. All right. So we've gone through, looked at the work, analyzed it, found our mistake. We corrected the mistake. Then we checked our answer to verify that that is correct. It is indeed correct. And so now we're guaranteed of getting the answer correct and getting all of our points. All right, and then the last problem. This is really out of left field. I think the reason why we are revisiting box plots is because our next chapter is going to involve us integrating what we've learned in algebra with some data statistics strategies for solving problems. Okay, so let's reacquaint ourselves with how box plots work. The box plot shows you not all of the individual scores for grades, but it does show you the minimum. It shows you the maximum. I'll go ahead and label these guys. The minimum and the maximum. And you've got your median, which is right here in the middle. And then you've got your quartiles. Your first quartile, which we sometimes call the lower quartile, and your third quartile, which we often call the upper quartile. Okay, so remember, all of this data represents 25% intervals of our data. Or I should say this box plot represents the 25% intervals. That's why they call them quartiles, right? Here's a quarter of the data, here's a quarter of the data, here's a quarter, and there's a quarter. All right, so looking at this, you know that 50% of the data is found in this inner quartile range. So you think as the median as an average, right? But that's just a single number. There's your median. But if you wanted to broaden that out a little bit, you could say, all right, well, the middle scores are between 74 and 90. Okay, so if you think of it as a broader range for your average, that's what that inner quartile range is all about. All right, so now that I've thoroughly looked at this box plot and have interpreted what those numbers mean, now let's answer the questions. What was the median score? Well, there's the median right there. What were the highest and lowest? There's your minimum, there's your maximum. Most of the students earn a particular score. We can't know that because we never see the individual scores on the box plot. We only see these 5 data points. If Ms. Sanchez had 32 students in her class, about how many students earned a grade of 80% or higher? Okay, so 80% or higher represents 50% of the data. 80% or lower represents 50% of the data. So you would say about 16 students, that's about half, right? Half of 32 is 80%. And then how many scored 90 or higher? Well, this is 25% of the data. So 25% of 32 is 8. We don't know the individual scores. We honestly don't know if 7 students scored hundreds and 1 student scored 90. We really don't know that. In fact, nobody may have scored 90. The only score that we know for absolutely certain is someone scored 100 and someone scored 55. But everything else, these are all medians, and so they may or may not have students that have those individual scores. And then, can you tell if scores between 80% and 90% were closer to 80 or closer to 90%? And the answer, once again, is no. You don't know any individual scores. You just know these main points, these medians here, okay? So just to reiterate, this number right here is the median of the entire data. This number right here is the median of the lower half of the data, and this number right here is the median of the upper half of the data. First quartile is the median of the lower half. The third quartile is the median of the upper half. All right, does that do it for today's work? It does. Let's move on to our next activity. Oops, what am I doing here? What am I doing? Okay, bye.
Hey, feeling good, like I should. When in dark, walk